Hello, grade 12 chemistry students. This week we're starting to look at naming hydrocarbons. Last week you guys took a look at the lessons and learned a little bit about the chemistry of life, why carbon is essentially the backbone of all life on Earth. Carbon is a unique, non-metallic element that can make a bond with up to four other elements or four other atoms. Uh, Unlike all of the elements below carbon on the periodic table, carbon is not a metalloid and it's not a metal. So it's relatively electronegative and it shares the electrons with other atoms. It's the most common one you're going to see bonded to carbon is hydrogen, or H. And when you see organic molecules drawn, like the ones in the lesson that I hope you guys have reviewed before you check out the video, um, you'll notice that often we don't show the hydrogens that are attached to the carbons. And that's because we assume that if a carbon is not attached to something else that isn't hydrogen, then all of its free electrons that are waiting to bond are attached to hydrogens instead. We're going to get to that in a minute when we look at these simplified Lewis diagrams. Let's start by naming some basic alkanes. Alkanes always contain only single bonds. So you're not going to see any double lines on alkanes. You're only going to see single lines like this. And hydrogen can only have single bonds anyway. So you're only ever going to see single lines between hydrogen and anything else. Now I'm going to pop the naming chart up there. As you can see, you guys should be able to name molecules with carbon chains of at least 10 carbons. Like this one here that has 2 carbons on it. Okay, so you see a carbon chain of 2. The prefix for 2 is F, so we would call this ethane. Okay. We use ane because it's only single bonds, and we use F because it's 2. The one below it is another Lewis diagram that contains all the carbons. Now again, count up the number of carbons that are here. We've got 1, 2, 3, 4, but you'll notice that the fourth carbon connects back to the first carbon. Now, if you remember from the lesson, we call this a cyclic molecule, which means basically the carbons have formed a ring structure. 4 carbons is still butane, but because it's cyclic, we're going to rename it instead as cyclobutane. All right, so cyclo because it has a ring, bute because there are 4 carbons in that ring, and ane because it's all single bonds. Right, cyclobutane. Now these ones over here are what are known as simplified Lewis diagrams, and I'll be honest, the more that you do organic chemistry, the more you are going to appreciate these kinds of diagrams, because drawing out diagrams like this takes a really long time. As a simplified Lewis diagram, we assume that every corner contains a carbon, right? So this here is a carbon, and the carbon has 3 hydrogens attached to it. This carbon here is another carbon, and it's attached to this carbon, and because the other 2 bonds need somewhere to go, it attaches to 2 hydrogens. So we got carbon, 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 okay? And that's 1, 2, 3, 4, 5, 6. So you guys know that 6 carbons means hex, and you notice that there are absolutely no double or triple bonds in there. So this must be hexane. Hex meaning 6, ane meaning single bonds. Okay. And it's not cyclohexane because carbon number 6 does not loop around and connect back to carbon number 1 again, like it did over here in cyclobutane. Both of these diagrams are correct and identical. Personally, when you guys are doing quizzes, activities, assignments that involve organic chemistry, I don't care what diagram you decide to include. Whether you want to do the full Lewis diagram, the simplified Lewis diagram with the hydrogens, or my personal favorite, a bunch of lines, which is also just a simplified Lewis diagram. It doesn't matter to me. Whatever makes the most sense to you guys and is going to be able to get the point across, I'm going to be fine with that. All right, so use whatever form diagram makes most sense to you. Now, alkenes have what are called double bonds. A carbon as you guys know, can bond with four things. But sometimes the carbon decides to bond to another carbon twice instead of just once. And we can show these bonds with a double line in between two carbons. This carbon here and this carbon here are sharing two bonded pairs of electrons instead of one. Now, what does this mean? Well, this carbon out here now only has space for two more hydrogens. Whereas this carbon here, again, has space for one hydrogen because it's also attached to another carbon. And you'll notice this little line that I drew down here, which I just wanted you guys to ignore. So let me just cross that out. There we go. That's like nothing. This is nothing. There, nothing. Pretend that's not there. I don't have any white out, so I wasn't able to remove it from my page without redoing everything, and I didn't really feel like that. And then this carbon over here is attached to three other hydrogens and a single bond to the one. Now, there are same naming rules as before, okay? The only suggestion is once there's other stuff beyond just an alkane is to number the carbons in your molecule just to be careful, right? So I might put a 1 there, a 2 there, and a 3 there. Now, since there are 3 carbons, we are still going to call it prop for prop or 3. And instead of ane at the end, because we have a double bond there, we're going to change the ane to an ene. Okay, meaning we've got a double bond here, and prop meaning 3. And we end up with propene. Kind of a funny name. Let's look at the next one. Things get more complicated once alkenes have more than 3 carbons because it's not enough here. Go, let's label these. 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 carbons in my molecule here, so you know that this is going to be an oct molecule because oct is the prefix for 8. Now it's very tempting to just go, oh, well, this is octene, right? Yeah. Looks good. I got a double bond. It must be octene. But the problem is this doesn't tell us where the double bond goes, right? The double bond could be here. It could be here. It could be in between these ones. It could be in between these ones or these ones or these ones or any of these bonds could be where the double bond is. So octene doesn't give us enough information about where the double bond goes. So I'm going to erase the ene. Don't worry, we're still going to use the ene, but before I write the ene part, I'm going to tell the reader which carbon, or the number of the carbon where the double bond begins. So if I look here, I've got this double bond starting on carbon number 2. So instead of just going ene, I'm going to put a dash 2 and another dash after the oct, and then I'm going to put ene at the end. Because that tells me where the location of that double bond is. It starts on carbon 2. Here's a double bond. There's 8 carbons total, and this is where the double bond is. The next one, we have to be very careful about how we number it. Part of the issue with numbering molecules is when you use numbering systems for organic chemistry or organic molecules, you have to make sure that you number it in such a way that the numbers are going to be the smallest possible when you name it. Which means I can't start carbon 1 over here because the double bond is way closer to this side of the molecule. Now, remember, you could just take this whole molecule and rotate it around and you'd have the same thing. So what I'm going to do is start numbering from this side instead. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There we go. If I were to number from this side, I would end up with this being carbon number 6. And that would not make my numbers as small as possible. I know it seems really silly, but when you number these things, you have to make sure that your numbers are as small as you possibly can. And as I said, you can start counting from any side of the molecule that you like. It's up to you. Now there's 10 carbons in this chain, so we know this is going to be a dec molecule because that's for 10. The double bond starts on carbon 3, right? Remember, we're counting this way. So 1, 2, 3, that's where the double bond begins. So dec 3, and then ene at the end because of the double bond. Perfect. When we work with cyclic molecules, it's a little bit different because we don't have to indicate what number the double bond is on. Because if we were to number it, let's start here. 1, 2, 3, 4, 5. The only way to number this is by putting the bond in between carbons 1 and 2, because that's going to make the numbers as small as possible. But since it doesn't matter where the double bond would be, we could start the numbers anywhere in the molecule. We don't actually have to say where the double bond is, but we do have to say that this is a cyclomolecule. It's got 5, so you know that's going to be pent. And then you just go ene, right? Because it doesn't matter if the bond's here or here or here or here or here, because we can change where we start numbering the molecule to make those numbers as small as possible. So there's no point in putting a pent 1-ene in there, because, you know, it's always going to be on carbon 1. So there's no point in saying that the double bond is on carbon 1. Now, the last one to look at, guys, is alkynes. Alkynes have triple bonds, and much like alkenes, we rename them with the YNE ending instead of the ENE ending. The first one we have there only has 2 carbons, 1 and 2. Obviously, numbering is not important when there's only one place that the bond could go. So we would just call this ethyne. The same rules for alkynes apply to alkenes when it comes to cyclic molecules. So again, we can start numbering however we like. 1, 2, 3, 4, 5, 6, 7, 8. Sorry for my shoddy drawing. All right, so with that, we know it's a cyclic molecule. So we have cyclo, oct, and then ine for the triple bond that's there. Perfect. All right, here's another one where, again, we're going to have to name, we're going to have to number from the right side to keep our numbers smaller. 1, 2, 3, 4, 5, 6. You'll notice that when carbons are triple bonded in the middle of a molecule, there's no hydrogens attached because the carbons are bonded 3 times to each other, and they only have enough space to bond to 1 carbon on that side and 1 carbon on that side. So you actually end up with kind of a thin part of the molecule here where there's no hydrogen sticking out. All right, so this one has 6, so that is going to be a hex. And because it's larger, we need to indicate which carbon the triple bond is on. So we have hex 2 ine, just like that. Last one, I don't know why I did this twice, but same deal. Because this triple bond is closer to the right side of the molecule, again, we're going to have to name from the right side instead of the left side. Now, if that seems weird, just wait until we are putting 3 different things attached to this molecule, and then trying to figure out where the numbers go there. Don't worry, I'm not going to give anything too weird, but it's good practice now to get into naming and numbering them from the right side, based on where the location of the, let's call them abnormalities, the things that make it different from just an alkane. Alkanes are the base, and then we change the name as we make changes to the double or triple bonds or add things stuck to the sides of molecules or things like that. Now that one has 9 carbons, so this is going to be a none, right? And let's see, non, and then the triple bond is on carbon 4, and then we have ine. So we end up with non-4-ine or known 4-ine, however you want to say it. And that concludes our naming. Let's look at drawing some molecules from the name. Now I'm going to draw them in a variety of different methods, starting with just the basic Lewis diagram. So for butane here, you know, and again, you can draw the shape of the molecules technically, like they kind of like zigzag up and down, because that creates the proper like spatial location of all the carbons and hydrogens. But butane means 4. So we're going to have 4 carbons. Always start by drawing the basic carbon structure, and then you can fill in the hydrogens after. And it doesn't matter where you put the hydrogens. You can put one up there, one down there. You can put two on top. You can put three like this. I've seen all sorts of different ways of doing it. So you're all good. Cyclohexane here. I'll show you another way to do the Lewis diagram. So if we do a Lewis diagram for a cyclic molecule, like so we know it's cyclo and hex means 6. Sometimes you'll see people just put the hydrogens on the side. So each of these has room for 2 hydrogens, so you could just go CH2, CH2, and just put ANH2 on each of the carbons. That's technically completely fine. Again, if you want to save yourself a little bit of time, as long as it makes sense when you're drawing these molecules and I could read it and figure out what you're trying to do, you're going to be good. So don't sweat. The last one we're going to do is 3-heptine. Okay, hept means 7. I'm going to draw this one with the simplified Lewis structure. I'm going to try to make it as simple as possible. So 1, 2, 3, 4, 5, 6, 7. It's basically Wario's mustache. Now, the 3-heptine, it seems to indicate that there's a triple bond on carbon number 3. Now, it doesn't actually matter which side you make carbon number 1, 2, and 3. As long as it starts from one side and goes in subsequent order, you're all good. I'm just, for simplicity, going to start from the left. So this is carbon 1, this is carbon 2, here's carbon 3. So the bond on carbon 3 to the next one is triple. So you would essentially add 2 more lines to that bond there to indicate that there's a triple bond in between those 2 carbons. And if you want, you can add all of the little hydrogens to the structure, or you can literally just leave it like that. And any viewer would assume that these carbons here are filled with as many hydrogens as they need to get a stable octet. So it's entirely up to you. I hope that helps. If you have any questions about naming things, drop me an email. There's no quiz this week. Okay, there will be a quiz next week as we move into organic chemistry in a little bit more detail. This is the last unit of the course, so we're going to spend the majority of the rest of the semester talking about organic chemistry and organic molecules and looking at different applications of these amazing materials and dangerous materials in a lot of ways too. So sit tight, enjoy the rest of your week, keep working on the My Pet element assignment, and that's due next Friday, so it doesn't need to be done right away, but if you have any questions about it, drop me an email. Have a good one.